All right, so let's start with the homework first. So I do realize, yes, the way part of this was worded, it could have been a little confusing to set up part of the problem. So I'll go over everything, and I'll actually go over both instances in case you might have done the opposite of what was intended. All right, so here we have a plane is getting ready to land. It is currently flying at an altitude of 240 feet. So we got our airplane, right? It's flying. It is 240 feet high. And it is 5,200 feet directly to the landing strip, right? So over here, we got the landing strip. So the way this was worded, like I said, I can kind of see the if there's some confusion here. The 240 should have been straightforward. That's your the height, right? The vertical length. Now, when I say it's 5,200 feet directly to the landing strip, that means directly from the plane to the landing strip. That would be 5,200. Okay. I do understand if you thought that it would be the bottom. All right. So I'll go over the problem again with the 5,200 down here. And I'll, if you did it that way and you got that answer correct, I'll give it to you. Just because I was a little unclear with the definition. So we want to know, what is the angle of descent the plane should take? So here, again, we got to be careful. I'm just going to move this for a second. So angle of descent doesn't mean this angle, right? Remember, anytime we're talking about an angle, it has to do with a horizontal line. Let's fix that. Right, so I'm talking about this angle over here. So I want to know, what is the angle of descent? Now, there's two things that I can do. I can move my triangle, right? Because instead of looking at like this, I can move the vertical line over here. This would still be 240 feet. This would still be 5,200. And now you're dealing with this top half of the triangle. We've seen something like this before, though, and the other thing we can do is I can take this angle, and I know, because the way I set this line up and this line up, that they're parallel, I can move the angle down to that spot. Both of these situations give us the same trig proportions. All right, so I am going to get rid of this part, and we're going to deal with the upper triangle. All right, so I have the 240 over here, and I have the 52,000 there. Okay, either way, the 52,000, that wouldn't change in this example. But I don't need this right now. Right. So now that we got everything where it's supposed to be, with this angle here, the 5,200 is my hypotenuse. Okay, it's across from the 90 degrees, and that would be the case however you set up your triangle. This here would be our opposite. So we would have to use sine. All right, so we have the normal trig relation. Sine of theta is 240 over 5,200. To solve, or you could have written this right away, we can solve theta by finding the inverse sine of 240 over 5,200. Oh, my batteries are dying. So I'm just going to plug that in as we see it. 240 divided by 5,200. Well, that doesn't make sense, so that's okay. Let's double check our, oh, that's in degrees. Okay. So we have a really shallow angle of descent, and it's only 2.6 degrees. Right, so we got a while till we get down, right? So it's very slowly, it's not a very steep angle that we're traveling down. Okay, so that's if you had the 5200 there. Now, another way you might have interpreted it was we have the 2400 here, I'm sorry, the 240 there, and you might have had the 5200 down there. Okay, but again, no matter what our situation is, that's the angle that we're talking about, okay, or this angle up here. Right, those are equal angles. So if you had it set up like this, you wouldn't be using sine, you would be using tangent. Right, so we would solve for theta, and we'd have the inverse tangent of 240 over 5200. And let's calculate that real quick. And actually there we get almost the same angle. All right, we get 2.64. Right, if you want to be real specific, you can say that this is 2.65, and that's 2.64. But essentially, they're very close. Okay. Now, if you had your angle up here as your angle of descent, well, then that would get you a very different answer for both cases. So yeah, be careful with that. Right. It's been a while since we've also seen, angle of depreciation, angle of elevation. So I wanted to throw that in there too, just to keep your mind sharp. Right. Any questions about that, about the assignment? So, like I said yesterday, today we are continuing with some type of word problems, but now we're not going to be talking about straight up triangles, right? All the situations that we saw, excuse me, we were able to set up, thank you. We were able to set up some sort of triangle to solve our problem. Okay, well, the first type, do I want to do that? Maybe, we'll see. All right, the first thing we're going to talk about is something called harmonic motion. All right, so we're dabbling in a little bit of physics here, and that's what I like. So there are a lot of things in nature that follow what's called harmonic motion. One of the most common types, and I don't know if you guys are in physics right now, or if you'll be taking it next year, is the movement of a spring, right? Springs are interesting. I was going to say something, but I forgot. Okay. All right, so the situation that we're dealing with, we have some sort of spring with a weight attached to the end of it. Okay, and we either pull down on it and let go, or we push up and let go. Right, so this here we'll call the resting position, right? So that's if you just let the weight hang from the string and you don't touch it, right? You let it settle. So then you pull it down, maybe you pull it down 10 centimeters, right? So these are kind of, you know, like I'm not going to draw the whole spring, but the spring gets stretched out. All right, so here's our resting position. I'll put this line here for reference. So I pull it down 10 centimeters. Now, this example and most examples in physics that we learn on I'll say elementary level, but an introductory level, we don't worry about certain things like friction. Now, have you guys done any physics stuff?
No.
Some of us
No,
are
okay.
in physics and some of us are in
Okay.
biology.
So there's something in science called the conservation of energy, right? So energy cannot be created, or it will not just disappear. It goes somewhere, right? So we're putting energy into the system by pulling the spring down. Now, normally we have things like air resistance and friction that take away the energy gradually, right? So one of Newton's laws is an object at rest stays at rest unless acted on by an outside force, and an object in motion stays in motion unless acted by an outside force, right? So if I had like this little wheel thing and I pushed it along, right, without friction, it would go on forever until something stopped it. But friction is the force between two objects when they touch, when they interact with each other. And what happens is that friction takes away some of the energy of this wheel rolling, right? So if I push it, we know, right, as long as it's a flat surface, it's not going to go on forever, right? It will stop eventually because of friction. Now, with these experiments that I'm talking about, we pretend friction doesn't exist. Okay, so this is like in a perfect vacuum where no outside forces are affecting our experiment. So we take this, the spring, we pull down 10 centimeters. Now, what happens is the way the spring works, its reaction is it shoots up 10 centimeters, right? This isn't drawn to scale, right? But however far we pull it down, it shoots up, right? And that's part of the conservation of energy. It starts moving this way, right? And if you're in physics, it has kinetic energy, which slowly changes to potential energy. And then the potential energy slowly becomes kinetic energy, and it starts back down. And then it switches, and it goes up and down and up. And in a perfect vacuum, it will keep doing this forever and ever. So we can actually graph what's happening, right? So if I take a look at a graph of the position over time, right? We start at the resting position. We pull it down to its maximum. It gets, 10 centimeters. Or we push it up. And then we release it. It comes back to the center, and it goes back up 10 centimeters. And what do you know? We have a sine function, right? And in a perfect world, it'll keep bouncing up and down between 10 centimeters down and 10 centimeters up, and it'll do that forever, right? Which gives us our harmonic motion. Okay, so we can model the actions of a spring using trigonometry. Now, there's a few parts that kind of tie over that we see. We have a period. So the period's a little different. It depends on a few things, but it's the time it takes for it to go back to its original resting position, right? So if I pull it down, it goes to resting position, it goes up, and it comes back down, and that would be one full period. right? So a period of harmonic motion would be one full cycle. We still have the amplitude, right? In this case, okay, it's how far it's pulled, right? So here our amplitude would be 10 centimeters because that's how far we pull it down. Now we have a slightly new topic here. Something called frequency. And frequency is directly related, or I should say inversely related, to the period. So the frequency, we say, is the number of cycles per second. The period is how many seconds does it take to make one complete cycle, right? So they have a very close relationship, right? So let's put some more numbers to this, and let's take a look. All right, so it's going to be very similar to the diagram I just drew. So we have a weight at the end of a spring. Right, I'll keep that displacement the same. We'll keep that at 10 centimeters. Right, but now we're going to add an extra bit of information that it takes 4 seconds for the weight to make one full cycle. So if I wanted to just draw a quick picture, right, at 0 seconds, it's at the resting position. So that's its initial part. At 1 second, right, that's how long it takes us maybe to pull it down. At 2 seconds, it gets back to its original part, but it's on its way up. So at 3 seconds, it's all the way at the top. And then at 4 seconds, we return back to the middle. Right, so you can kind of see here how the sine wave is appearing right before our eyes, right, as time moves along, right? So that's 0 down here would be. Now, one caveat, the one part of debate is how to assign positive and negative distance. So a lot of times, if we're moving down, then it's negative, and if we're moving up, it's positive. But with the spring, if I pull it down, then I'm acting on it in a positive way. So this would be considered positive 10, and up here, what might be negative 10. What I'm just going to do is just say that it's 10 centimeters up and 10 centimeters down. Right, so here we have our period is 4 seconds. We said our amplitude was 10 centimeters. Now the frequency, I want to know say it again. Numbers of cycles per second. Right? So in 1 second, how much of a cycle do I go through? Right? So for 1 second, I move from here to here. Well, for one full cycle, that's 4 parts, right? 1, 2, 3, 4. So my frequency, we would say, is 1/4 cycle per second. Now you may notice the close relationship there. We can change okay, that's why I said it's inverse. The period is equal to 1 over the frequency, or we can say the frequency is equal to 1 over the period. All right, so if we know 1, we pretty much know the second one. All right, so how do we use this with trigonometry? Well, we see a lot of this similar terminology, right? We have amplitude and we have period, so that's going to help us. So with this, we can have the definition of simple harmonic motion. So the problem that we would look at is we want to find the distance or the position of the object in simple harmonic motion at any time, right? So if I want to find, at t equals 10.5, where will my weight be? Where will that displacement be? Okay. We can use either the distance is the amplitude A sine times omega t, or A cosine omega t, where A is our amplitude, right? So in our case up there, it would be 10. And omega is like our B that we saw before. Right? So our period would be the 2 pi over omega. And then with our new frequency, we can flip that, and we can say that the frequency is omega over 2 pi. Now, we choose between sine and cosine depending on how we start the problem. Okay, if we start here, we say, okay, we have a neutral start, which is what we saw, right? So we start in the middle, right? And then I pull down and it goes up and down. I would use the cosine if I'm starting at one of my maximums or minimums. So say the problem started off, well, we push the spring back all the way at time equals 0, and then we let it go, right? In that case, we would use cosine. And crap, I'm running out of time. All right, so we'll finish this up tomorrow. We'll finish talking about simple harmonic motion. And I know I threw a lot of variables and stuff at you. We'll make that a little more clear tomorrow. All right. So yeah, I won't give you any homework tonight since we're not really done discussing simple harmonic. All right, so we'll finish this up. We'll wrap it up tomorrow. Everybody have a good day, and I will see you later.
Bye, you too.
Bye, Mr. Murray.